Hello everyone, I'm Mingqing Kang from Hopkins University. Today I'm presenting scaling JavaScript abstract interpretation to detect and exploit Node.js Taint-style vulnerability. Taint-style vulnerability is the typical class of weakness where the input data reach sensitive things through unsafe path. Including OS command injection, these vulnerabilities can lead to severe consequences. In 2020, a Node.js package had a code injection vulnerability, leaving 7 million potential users in danger. In 2021, another Node.js vulnerability affected 8 million users per week. To prevent such vulnerabilities, one measure that developers can take is static analysis. Ideally, analysis should have both high scalability and high accuracy. However, no state-of-the-art approach can achieve both. Traditional syntax-directed approaches can have high scalability, but because of the lack of the support for dynamic features, their accuracy is low. By adding abstract domain, we got abstract interpretation approaches, such as ODGen, published in Usenix 22. They have high accuracy, but their scalability is low. Today, I'll talk about how we progressed towards ideal analysis. Let's see a motivating example. This is a compression utility that allows users to choose from multiple compression algorithms. If the user chooses the zip algorithm, it is implemented in a JavaScript function. If the user chooses the XY algorithm, it calls an external program. Here, promisify is a function commonly used in JavaScript that converts callback-based functions to promise-based functions. This example has an OS command injection vulnerability. The source is the parameter of the function compress. We assume that the attacker can control this variable. The sink is called at line 4, when fn is equal to child process.exec. Here, fn is a function passed as a parameter of the function promisify, which is also called a function pointer. There's another function call in the second function. The callee cannot be determined until the value of the parameter is known. These dynamic features are common in JavaScript, but they are not supported by traditional syntax-directed approaches. It requires abstract interpretation. However, abstract interpretation has its own limitations. For example, at line 9, the zip algorithm is a function that creates an exponential number of objects, slow down the analysis, and make the analysis unable to scale. Therefore, when analyzing the function compress, it will be stuck here. However, the sink needs to be reached through this statement, and thus the sink will never be reached. Our system design contains 3 stages. The first stage is lightweight. The second stage is heavyweight, but guided by the control flow path generated by the first stage. These 2 stages are to make the analysis scale. The third stage is to reduce false positives. Let's talk about stage 1, control flow path generation. The first step, bottom of abstract interpretation, starts from the functions at the bottom of the AST, which have the lowest scopes, and goes to the higher level functions. That's why it's also called scope-based. It generates control flow graph, call graph, and an intra-procedural data flow graph. The second step searches the control flow graph and the call graph. And the output of this stage is control flow path. Let's see how to work with the motivating example. At line 4, the function executor calls the function fn, which is the parameter of the function promisify. We don't know what the fn is until promisify is called. Therefore, we can create a dangling edge in the call graph and memorize how fn can be found from promisify's parameter. We say there's a function dependency between between promisify and fn. We can memorize such dependency in the function dependence graph, or FDG. At line 7, when ask a process calls promisify, although we still don't have a concrete value for the parameter, we know that fn can be replaced by child process method. Therefore, we can add another alternative lookup path and add such dependencies in the function dependence graph in the same way. At line 22, when compress calls execute process, we finally got the concrete value for the argument. We look up the FDG and find this dependency and the lookup path. Now we got a concrete called E. We can now add a concrete edge in the call graph, which is from executor to child process.exec, which is the sync function. Now we just look at the function compress. We know that the sync is reached through the second switch case. The first switch case, however, doesn't call the sync function, but leads to object explosion. We can skip those functions and branches that are not related to the syncs by a control flow path search. First, we search the function from the function's entry to this statement for a control flow path. Next, we use backward slicing by search the intra-procedural data flow graph and get data flow path. Finally, we can select the related statements by both control flow and data flow information. For example, this call to the logger will be ignored. Now let's talk about stage 2, data flow path generation. In this stage, we use the more traditional call-based top-down abstract implementation. It starts from the top-level file nodes and follows the call relations and the control flow path. That's why we call it top-down abstract implementation. It's branch-sensitive and generates object-level interprocedural data flows. The second step searches for data flow paths for both vulnerability detection and exploit generation. For example, at line 20, the function, the elements in the array are contained into a string. Therefore, we can add data flows from the function elements to the newly created string object and mark it with the operation type. Then it's assigned to the variable command. We also notice that these assignments happen under a switch case and an if-else condition. We can add and propagate those condition tags to the object relation edges. Then command is assigned to the parameter arg, which is the sync variable. Then we can mark the source objects and the sync objects and find a path between them. We also propagate the path to other related objects, such as the array elements. Now we talk about stage 3, exploit generation. In this stage, we convert the data flow path to constraints. In other words, we reconstruct the operations from data flow path. We use type principle here is because JavaScript is weakly typed, but the constraints are strongly typed. Then we use a constraint solver to solve variable values. Here we use the D3 solver. Finally, we can generate the code expressions and arguments with the solved variable values and other object relation information. Let's see how it works. First, we symbolize the objects. Then we can generate constraints for the content values and for the operations reconstructed from the data flow path. Next, we generate the constraints from the conditions. Finally, we can solve them with the constraint solver. Our implementation fast is implemented on top of ODGen with over 13,000 lines of Python and JavaScript code. We created 2 versions of the system. One with the first 2 stages has only vulnerability detection. The other includes the stage 3, automatic exploit generation. In our evaluation, we answer 5 questions: zero-day vulnerability discovery, scalability, false negative rate, false positive rate, and call graph accuracy. For zero-day vulnerability discovery, we prepared a randomly selected NPM package dataset. For scalability, we prepared a dataset of vulnerabilities in popular large packages over 10,000 lines of code. For false negative rate, we mixed the known vulnerabilities from prior works into a 391 package dataset. For the rest, we prepared another smaller NPM dataset. We compare fast with ODGen, our previous state-of-the-art abstract interpretation tool, CodeQL, a state-of-the-art syntax-directed static analysis, and the JS call graph, an open source tool for JavaScript call graph generation. Among 100K NPM packages, FAST finds 242 zero-day vulnerabilities that are not detected by state-of-the-art tools. We got 21 CVE numbers so far. FastEXP automatically exploits and helps human verify half of the detected vulnerabilities. We responsibly disclosed these vulnerabilities to developers and give them 45 days for fixes. Large packages are challenging for abstract interpretation. FAST detects 11 out of 14 vulnerabilities in large packages, while ODGen detects 0, which means FAST scale to large packages that ODGen cannot handle. In terms of vulnerability detection, FAST has lower false negative rate and false positive rate than state-of-the-art tools. Thanks to automatic exploit generation, FastEXP has a 0 false positive rate. Finally, we manually compared the generated call graphs. FAST finds more correct edges than state-of-the-art tools. FAST is open source. Don't forget to check our GitHub repository and our paper. Thanks for listening to our presentation. Any questions?
Questions? I have one question for you. Could you go to slide 45?
45?
Yeah.
Sure.
So the fast exploit has higher false negative rate compared to the other tools. Can you explain why that is the case?
That's a great question. Because FastEXP because when a vulnerability is exploitable, FastEXP will regard that as a detected vulnerability. That's why we have a higher false negative rate than other tools.
Also, why does it have higher false negative rate compared to fast that?
Because only if it can automatically exploit that vulnerability, it will regard that vulnerability as detected. So if the vulnerability is not exploitable, they will say this vulnerability is not detected. That's why a lot of existing vulnerabilities are not detected, and thus it has a higher false negative rate.
Okay. Any other questions? Okay, then thank you very much.